All right, let's jump right into this deep dive. You've sent over some really interesting AI research. Looks like you're exploring advancements in several areas. We've got a whole mix of articles straight from rxeki.org. That's where researchers share their fresh findings covering computer vision, natural language processing, and even some applications in healthcare and cybersecurity.
Yeah, it's pretty fascinating to see how AI is really impacting so many different fields.
Absolutely. And one that caught my eye right away, this paper on multimodal prescriptive deep learning. They talk about these things called PNNs, prescriptive neural networks. Sounds pretty futuristic.
It does, doesn't it? So KNNs, what they are is a combination of optimization and deep learning techniques. What they do is they analyze data from multiple sources, let's say medical images, along with a patient's records, and then they actually recommend treatments.
So instead of just saying, here's what's going to happen, these networks can actually say, here's what you should do.
Exactly. And get this, the researchers tested these PNNs on real medical data, things like aortic valve replacements and liver trauma cases. And you know what? Their recommendations could really significantly reduce things like estimated complication and mortality rates.
That's incredible. That has huge implications for personalized medicine, right?
Yeah.
Treatments tailored to a patient's own unique situation.
Absolutely. And there's more. They were actually able to extract interpretable rules from these PNNs, which is essential in medicine. Doctors need to know the why behind a decision, not just blindly follow what a machine says.
That makes a lot of sense.
Yeah.
So AI isn't just predicting the future, it's starting to guide what the future should be. Let's switch gears a bit now, talk about bidirectional curriculum learning. This one focuses on spotting anomalies in graph data. Think social networks, financial transactions, that sort of thing.
Right. So this method, it really helps us identify those unusual patterns in networks. They call it dual focus because it looks at both homogeneity and heterogeneity within a graph. Basically, how something deviates from both what's typical and atypical behavior at the same time.
So it's not just saying this is an outlier, it's saying here's how it's an outlier and why that's important.
Precisely. It's more nuanced, more intelligent. Think of a security system that not only detects an intruder, but analyzes their movements to tell if they're amateur or professional. That's the level of understanding we're talking about.
Fascinating. They're really creating AI that can see those subtle differences that might get missed otherwise. Okay, there's also this paper on advances in temporal point processes. It looks at different ways of analyzing events that happen over a period of time. What surprised me is they're talking about LLMs being used for this. LLMs, aren't those mostly for text and language?
You'd think so, right? It does seem a bit unexpected. But you see, LLMs have this knack for grasping complex relationships and contexts, and that makes them surprisingly well-suited to understanding how things unfold over time.
So instead of seeing events as just isolated incidents, they can actually connect the dots and understand the dynamics at play.
Exactly. It's like having an AI that can see the whole story, not just individual chapters. Imagine, for instance, an LLM analyzing a patient's medical history. It wouldn't just see a list of appointments, it would see the progression of an illness. It could maybe even anticipate future health outcomes.
Now that is powerful. Okay, shifting gears again, let's talk distributed conformal prediction via message passing.
That one is about ensuring accurate and reliable predictions. And this is really important, especially in fields like healthcare, where being right is absolutely critical. What they use here is something called conformal prediction. It's a way of making prediction sets that come with very strong statistical guarantees.
Now the term distributed, that suggests we're talking about multiple devices working together. Is this relevant to scenarios where data might be spread across different sources?
Precisely. Let's say you have a network of medical devices, each one having only a small piece of the patient data puzzle. With this research, these devices can actually pool their information together. You get this collective intelligence, a much more reliable prediction than any single device could manage on its own.
It's like they're creating a team of AI detectives, each one bringing their own clues to solve the case.
That's a great way to put it. Now, this reminds me of another paper that touches on this idea of knowledge sharing, but on a network level. The paper is titled Community Detection for Contextual LSBM, and it digs deep into network analysis.
Okay, what's different about this approach?
This research is about how we can accurately pinpoint communities within networks. The key here is context. They're not just looking at the structure of a network, but the attributes of each individual node.
So it's not just about who is connected to whom, but also about why they're connected. What are their shared interests, backgrounds, anything that might lead to the formation of a community?
Precisely. Think about social networks. People form groups around shared interests, not just random connections. This research provides a framework for understanding these community structures with that deeper context in mind.
And that could apply way beyond just social media, right? Biological networks, financial markets, anywhere those intricate structures exist.
Absolutely. This research gives us both theoretical and practical tools for analyzing these complex systems, and they've even developed an algorithm specifically designed to work with this contextual model. It's a spectral-based algorithm. While it may not be perfect, it lays the foundation for even more powerful tools down the line.
So a deeper understanding of how communities form and function. All right, let's tackle sample complexity next. This paper caught my eye. On the sample complexity of one hidden layer networks with equivariance, locality, and weight sharing. The title is a bit of a mouthful, but the idea of sample efficiency in deep learning really intrigues me. What's the big takeaway here?
This paper digs deep into how specific design choices in neural networks actually help them learn effectively, even when you have limited data. Think about convolutional networks. Those are commonly used in image recognition. They rely on things like weight sharing and local filters, and this paper argues those are crucial for their sample efficiency.
So these design elements, often we just take them for granted, but they're actually playing a crucial role in making these networks good learners, even without huge data sets.
Precisely. They focus on single hidden layer networks and how much data they need to generalize well. And what they found is that weight sharing can achieve surprisingly similar results to its more complex counterparts, but it all depends on the specific mechanism. They also found that locality is essential, meaning networks with these local filters actually need fewer samples. But there's a catch that can limit their ability to capture really complex patterns because of something called the uncertainty principle.
Wait, hold on. The uncertainty principle.
Yeah.
Isn't that from quantum mechanics?
Yep, that's right. Might seem strange, but the same principle that limits measurement in quantum mechanics, it actually applies here too. It shows the trade-off between locality and expressivity in neural networks. Who knew?
That's wild. It just goes to show how these seemingly separate fields can actually be connected in some really deep ways. All right, enough of that deep stuff. Let's move back to computer vision. In a world that, frankly, sounds a bit unnerving. Device-aware optical adversarial attack for a portable projector camera system.
It does sound a bit like something out of a spy movie, doesn't it? So this research explores a particular kind of attack. Think face recognition systems, but instead of hacking the software, they use a projector camera system. They project carefully designed patterns of light onto someone's face to fool the system.
And the device-aware part suggests this isn't just some simple trick. What makes this different from other attacks?
A lot of these projector camera attacks, they don't really work well in the real world. Why? Because of things like variations in device resolution or how colors are reproduced. This research takes those real-world quirks into account. They've developed an algorithm that can actually adapt to things like resolution and color.
So they're essentially bridging the gap between the digital attack and the physical world, making it a lot more effective.
Exactly. And they tested this against commercial face recognition systems with, I have to say, pretty impressive results. This highlights a real vulnerability that definitely needs addressing.
It's a constant cat and mouse game, isn't it?
Hmm.
As these systems become a bigger part of our lives, understanding these vulnerabilities and how to counter them becomes more and more important. Okay, one more for this section. This one looks at medical imaging again. Revisiting CLIP, efficient alignment of 3D MRI and tabular data using domain-specific foundation models. What's the main challenge they're tackling here?
The big challenge here is integrating different types of medical data. You've got 3D MRI scans, which are very visual, and then you have all that tabular data from patient records, lots of numbers and categories. Combining these two can give us a much more complete picture of a patient's condition.
So they're bridging the gap between what we see in the scans and the numbers in the files. I see they're talking about CLIP, that model that usually aligns images with text. How does that work here?
What they've done is really clever, actually. They've taken CLIP's core principles and adapted them to the medical world. Instead of that generic image encoder, they've trained a specialized model specifically on MRI scans. So it's learning the language of medical images.
It's like CLIP went to med school and specialized in radiology. So now it can actually understand those complex MRI scans.
Exactly. And here's the amazing part. They did this with a very small data set, only 62 MRI scans. It really highlights the potential of this approach.
I can see how this could revolutionize medical data analysis. more accurate diagnoses, personalized treatment plans. It's truly remarkable.
Yeah, it's a reminder that even in research, the tiniest details matter. A small error can snowball into something that really skews our understanding of AI, both its strengths and its weaknesses.
For sure, it's a constantly evolving field, so being careful and really double-checking our assumptions is super important. Okay, let's dive into a paper that's very relevant to our current world. Mitigating Gen AI-powered evidence pollution for out-of-context multimodal misinformation detection. That title's a mouthful, but this Gen AI-powered evidence pollution, this sounds concerning.
It is. This research looks at how misinformation campaigns are becoming more sophisticated. They focus specifically on what they call out-of-context multimodal misinformation, where images are basically repurposed to create a false narrative.
So not just manipulating what's already out there, but actually creating entirely new images to back up false claims.
Exactly. Imagine a completely fabricated image of a protest, something generated by AI, being used to spread misinformation about a political event. It's easy to see how that kind of polluted evidence could spread online and fool people.
It's a scary thought. It feels like we're in an arms race against misinformation, and AI is being used on both sides. What are they suggesting we do to counter these tactics?
They've come up with two main strategies. One is called cross-modal evidence re-ranking. It prioritizes evidence from trustworthy sources by considering both text and visuals.
So like training an AI to be a fact checker, able to sift through all the noise and point us to reliable information?
Exactly. And the second strategy is cross-modal claim evidence reasoning. This looks at the consistency between what's being claimed and the evidence being presented, like a detective trying to make sure all the pieces of the puzzle actually fit.
A multi-layered defense system against misinformation. This research is crucial as AI-generated content becomes harder and harder to distinguish from reality. Okay, let's shift gears and talk about a technical challenge in infrared imaging. ASNATE, Asymmetric Sampling Correction Network for Infrared Image Striping. Can you explain what these striping artifacts are and how they're addressing it?
So striking artifacts, those are basically unwanted vertical lines that you sometimes see in thermal images. Imagine trying to look at a thermal image, but there are these annoying lines obscuring the details. They happen because of inconsistencies in the sensor's response.
So they're essentially developing a method to clean up these images and remove those distracting stripes.
Exactly. They've developed a deep learning model called ASCNet that specifically targets this issue. The heart of it is something they call asymmetric sampling correction, a fancy way of saying it can capture and correct for those inconsistencies across the image.
I can see why they needed a fancy name for that.
Yeah.
So how does this affect the final quality of the images?
They tested ACNet on both simulated and real-world data, and the results were impressive. It actually outperformed existing methods, effectively removing those stripes and making the infrared images much clearer. This has huge potential in areas like surveillance, remote sensing, even medical imaging, wherever infrared is used.
It's fascinating how deep learning is being used for these highly specialized image processing tasks.
Mm-hmm.
All right, let's talk about a paper that deals with analyzing massive medical images. Premix, addressing label scarcity and whole slide image classification with pre-trained multiple instance learning aggregators. First off, what are whole slide images and what makes them so challenging to work with?
Whole slide images, or WSIs, are basically extremely high-resolution digital versions of those microscopic slides used in pathology. We're talking billions of pixels capturing an entire tissue sample. Just imagine the size of that image. Analyzing them for diagnosis or research is a massive task. You need expert knowledge and a lot of time.
So they're trying to use AI to automate this process and make it more efficient.
Yes, and the specific challenge they address here is WSI classification. That means assigning a label to the entire slide, like saying whether a disease is present or not. The problem is, getting these massive WSIs labeled is incredibly time-consuming and expensive.
So they need a way to make the AI learn effectively, even when there's limited labeled data.
Exactly. Their solution is called Premix, and it uses something called multiple instance learning, or MEL. MELL is perfect for WSIs because you don't need super detailed annotations for every tiny part of the image. It can learn from those slide-level labels, like a simple yes or no.
So instead of needing a pathologist to label every single cell or structure, you can just tell the AI whether the slide as a whole shows a particular feature. That makes a lot of sense.
Right. And Premix takes it a step further by using pre-trained MIL aggregators. These are components that have already learned to extract important features from WSIs. They're like those experienced analysts who can spot patterns without needing to be told exactly what to look for.
That's a clever way to leverage existing knowledge and get the most out of the limited data you have. It seems like this could really speed up research and diagnosis in pathology, being able to analyze huge WSI datasets. So how does premix perform compared to other methods?
The results are really promising, especially when you only have a small number of labeled WSIs. It consistently outperforms other methods, which suggests it could make WSI analysis much more accessible for researchers and doctors.
This is a great example of how combining innovative techniques like MIL with these pre-trained models can solve real-world problems in healthcare. Now let's jump into a paper that brings AI into the natural world. In situ fine-tuning of wildlife models in IoT-enabled camera traps for efficient adaptation. This sounds like an exciting application.
It is. They're using camera traps equipped with AI to monitor wildlife populations. The problem is these traps are often in remote areas with limited connectivity and power. And traditional deep learning models, those that are trained on carefully curated datasets, they don't always adapt well to the ever-changing conditions of the real world.
So the AI might misidentify animals because the lighting, weather, or even the vegetation in the camera trap images are different from what it was trained on.
That's the problem. Imagine an AI trained to recognize a specific bird, but the lighting in the forest changes throughout the day. It might not recognize the bird anymore, so they need to teach these systems to learn and adapt on the fly.
The sort of learn-as-you-go approach.
Exactly. They came up with something called WildFit, which is an autonomous adaptation framework. It allows these models to constantly learn and become more accurate, even in these tough conditions.
Okay, how does it actually do that?
Well, they realize that the background scenes in these camera trap images change a lot more frequently than the animals themselves do. So WildFit takes advantage of that. It actually generates new training examples right there on the device, combining images of animals with new background images from the camera trap.
So it's creating custom training data specifically for that environment. That's very clever.
Right. And to save energy and bandwidth, it only updates the model when really necessary. The results are great, much better accuracy while using minimal resources.
That could really revolutionize wildlife monitoring. Imagine a whole network of these AI-powered cameras constantly adapting to their surroundings, providing much more accurate data about animal populations.
And that data can then help researchers make better decisions about conservation.
A fantastic example of AI being used to help protect our planet. Now, let's move on to a paper that explores how different AI models can learn from each other. Multi-aspect knowledge distillation with large language model. What's knowledge distillation all about, and why is it so important?
Knowledge distillation is like having a student learn from a more knowledgeable teacher. In AI, the teacher is often a very powerful LLM, and the student is a smaller, more efficient model.
So they're trying to transfer the expertise of the larger model to the smaller one.
Yes, but this research takes it a step further. It focuses on multi-aspect knowledge. Traditional knowledge distillation might just teach a model to identify an object, but multi-aspect knowledge provides more information about the object beyond just its name.
Like teaching it not only that it's a cat, but also about typical cat behavior, habitats, things like that, giving it a much richer understanding of the concept.
Exactly. They do this by asking the LLM specific questions like, what are the typical behaviors of a cat? Or what are the different breeds of cats? Then they use the LLM's answers to teach the student model.
So you're essentially taking all the knowledge from that vast LLM library and distilling it into something more concise and easier to work with. How well does this approach actually work?
It works really well. They found that it significantly improves the student model's performance on a variety of tasks, like image classification and object detection.
That suggests LLMs can be incredibly valuable teachers, sharing their knowledge with other AI systems and collectively advancing the field. It's like creating a network of AI minds that can learn from each other.
That's a great analogy. It really shows the potential of AI systems working together. Now, let's talk about a platform designed to make AI more inclusive. Funar, an Arabic-centric multimodal generative AI platform. What makes this platform unique and why is it so significant?
It sounds like a major step towards making AI more accessible to Arabic speakers. What else can Funar do?
Funar isn't just about text. It has speech recognition for a variety of Arabic dialects. It can synthesize speech and even generate images that are specific to different regions. It's a whole toolkit designed specifically for the Arabic language.
It sounds like a well-thought-out and culturally sensitive AI platform. Any features that really stand out as particularly innovative?
They have a customized Islamic retrieval augmented generation system, or RH system.
Mm.
It's specifically for answering questions related to Islamic topics in an accurate and culturally appropriate way. It really shows the level of detail they've put into making this platform relevant for its target audience.
It highlights how important it is to consider cultural context and make sure AI tech is developed and used responsibly. What other features help to ensure that FANR is reliable and trustworthy?
They have an attribution service that verifies the authenticity of the content that's generated. That's essential for combating misinformation. It allows users to trace the sources of information and see if it's credible.
It's all about promoting responsible use of AI. FANR is a fantastic example of how AI research is becoming more globally relevant and inclusive. Let's move on to a comprehensive survey on integrating large language models with knowledge-based methods. What's the motivation behind combining those two approaches?
LLMs are amazing at generating human-like text, but they're not always perfect when it comes to factual accuracy or complex reasoning. Knowledge-based systems, on the other hand, are designed for representing knowledge in a structured way, using things like ontologies and knowledge graphs.
So it's like having the fluency of a talented speaker combined with the depth of knowledge of an expert in that field.
A perfect analogy. This survey looks at how integrating these two can enhance AI systems. They talk about improvements in data contextualization, increased model accuracy, and better use of knowledge resources.
It seems like a powerful combination. What are some potential applications where we might see the benefits of this integration?
Think of a chatbot that not only understands your questions, but can also pull up relevant information from a vast knowledge base to give you accurate answers, or a medical diagnosis system that can consider a doctor's observations along with structured medical knowledge to make a more informed decision.
It's about making AI systems smarter and more trustworthy. Okay, let's move on to a paper that explores the use of AI in mental health care. A layered, multi-expert framework for long-context mental health assessments. What specific challenges are they tackling in this research?
This paper is about using LLMs for mental health assessments, specifically ones that involve analyzing lots of text, like transcripts from therapy sessions or interviews. Traditional LLMs, as good as they are at generating text, sometimes struggle with staying consistent over long stretches of text. And they can sometimes hallucinate or generate text that sounds plausible but isn't accurate or relevant to the context.
So they need a way to make these LLMs more reliable and sensitive to the nuances of human conversation, especially in the context of mental health.
Exactly. They introduced something called stacked multimodal reasoning, or SMMR. It's a layered framework that uses multiple LLMs and specialized smaller models. Each model acts like an expert, focusing on a specific part of the assessment.
So it's like having a team of AI specialists working together to reach more comprehensive and reliable diagnosis.
Precisely. The early layers might identify specific symptoms or patterns in the text, while later layers take all that information and use it to understand the person's overall mental state.
And how does this multi-expert approach compare to using a single LLM?
The results are very encouraging. SMMR is much better at reducing those hallucinations, capturing the subtle details in the text, and producing more accurate assessments.
This could be a game changer for mental health professionals. Imagine having AI assistance in diagnosis, treatment planning, even monitoring a patient's progress. It's a sensitive area, but this research shows how AI can be applied thoughtfully and responsibly. Okay, next up. The dual-use dilemma in LLMs. Do empowering ethical capacities make a degraded utility? What's the dual-use dilemma and how does it relate to LLMs?
This research delves into a fundamental challenge in responsible AI, balancing safety with functionality. The dual-use dilemma refers to the fact that technology developed for good can also be used for harm. LLMs, with their vast knowledge and ability to generate new content, are a perfect example of this.
The classic double-edged sword of powerful technology. So how does this play out with LLMs?
LLMs are trained on massive datasets, and those datasets inevitably contain both positive and negative aspects of human behavior. This means LLMs can learn to generate harmful content, even if it's not what the creators intended. The challenge is to find a way to give LLMs a sense of ethics and responsibility without limiting their capabilities.
It's like trying to teach these AI systems right from wrong. Does this research suggest that making them more ethical will necessarily make them less useful?
That's what they set out to investigate. They developed a framework for aligning LLMs, training them on a special data set that includes both legitimate and illegitimate requests. And they added a rephrasing mechanism to make sure the models really understand these sensitive concepts.
So they're trying to guide these LLMs towards making ethical decisions without restricting them too much. What were the results?
The results are actually very encouraging. Their LLM, called LibraChem, performs better than existing models in both safety and utility. It seems like it might be possible to achieve both, after all. This research offers a path toward LMs that are powerful and responsible, which is essential if we want to harness AI for good.
It's a hopeful sign that we can create AI that aligns with our values.
Mm.
Now, let's move on to ZEP, a temporal knowledge graph architecture for agent memory. Why is memory considered such an important part of AI, and how does ZEP address the limitations of current systems?
Memory is crucial for intelligence. It allows us to learn from past experiences, understand the present, and make decisions about the future. This research is about giving AI agents, like those chatbots or virtual assistants, a better memory system. Traditional AI agents often rely on simple retrieval mechanisms or predefined knowledge, which limits their ability to adapt and have meaningful conversations.
So they're trying to make AI systems that can remember and learn from their interactions, just like humans do.
Exactly. ZEP uses a novel component called graffiti. It's a temporally aware knowledge graph engine, which means it understands the concept of time. It dynamically combines information from both unstructured conversations and structured business data. Imagine an AI assistant that remembers your past interactions and uses that knowledge to give you more personalized and relevant responses.
It's like these AI systems are developing their own mental timelines, incorporating their experiences into how they understand the world. So how does ZEP compare to more traditional memory systems?
ZEP significantly outperforms existing systems, especially when it comes to tasks that require complex reasoning about time. This research has the potential to make AI systems much more human-like in their interactions, allowing them to understand the flow of conversation and use past experiences to make better decisions.
It's a big step towards creating AI that can really understand the nuances of human interaction. Let's switch gears now and look at AI's role in medical education. Benchmarking generative AI for scoring medical student interviews and objective structured clinical examinations, OSCEs. What are these OSCEs and how is AI being used to improve them?
OSCEs are standardized tests where medical students are evaluated on their clinical skills and communication abilities. They interact with actors who are pretending to be patients. Traditionally, human examiners score these interactions, which can be time-consuming and potentially subjective. This research is about using LLMs to automate the scoring process.
So they're training an AI to be like a virtual examiner, hopefully providing more objective and consistent assessments.
That's the idea. They took a data set of OSCE transcripts and the scores given by expert examiners, and they used that to train and evaluate 4 different state-of-the-art LLMs: GPT-4o, Claude 3.5, Llama 3.1, and Gemini 1.5 Pro.
It sounds like a pretty thorough test of how well these LLMs can understand these complex medical interactions. So how do they do?
They're not perfectly aligned with the human examiners yet, but they're getting there, especially when you look at certain metrics like off-by-one accuracy and thresholded accuracy. It suggests that LLMs could be a valuable tool for making OSCE evaluations more efficient, consistent, and potentially less biased.
It's an interesting application of AI in education. It could really change how we train and evaluate healthcare professionals in the future. Let's talk about a paper that tackles a major challenge facing online platforms towards safer social media platforms, scalable and performant few-shot harmful content moderation using large language models. Why is this research so relevant today?
Social media platforms are constantly battling harmful content, and it's a huge challenge to keep up with the massive volume of user-generated content. Traditional approaches like human moderators are expensive and can be very emotionally draining. Supervised machine learning requires tons of labeled data, which is a big hurdle. So this research looks at using LLMs and few-shot learning to address this problem.
So instead of relying on armies of human moderators or building huge data sets, they're using the power of LLMs to learn from just a few examples.
Exactly. This few-shot learning is key. It allows LLMs to adapt quickly to new types of harmful content without needing huge amounts of data. Imagine an LLM that can recognize a new form of hate speech or cyberbullying based on just a handful of examples.
That level of adaptability is essential, given how quickly things change online. How does this LLM approach compare to existing moderation systems?
It actually outperforms existing systems, even those commercial ones like Perspective and OpenAI moderation. And they've even explored adding visual information like video thumbnails to make it even more accurate.
It's impressive. It sounds like LLMs have the potential to make a real difference in making online spaces safer. Now, here's another paper addressing the same challenge but with a different approach. Re-ranking debation reading using large language models for mitigating exposure to harmful content on social media platforms. How is this one different?
Instead of trying to remove the harmful content outright, they're focusing on changing how the content is ranked and displayed.
So manipulating the algorithms that control what we see in our feeds to make the harmful stuff less visible.
Exactly. Social media platforms use algorithms to personalize what users see, but sometimes those algorithms can inadvertently promote harmful content. This research suggests using LLMs to assess how harmful content is and then re-ranking it accordingly so it's less likely to show up in people's feeds.
It's like they're trying to instill a sense of responsibility into those algorithms, making them prioritize safer and more positive content.
And they're doing it by taking advantage of the zero-shot and few-shot learning abilities of LLMs. That means they can train these models on a relatively small number of examples, which is essential because you can't possibly anticipate every type of harmful content that might appear online.
It's a delicate balancing act, trying to promote positive content without resorting to censorship or limiting freedom of expression.
Absolutely. It's a complex issue with ethical and social implications that need to be considered very carefully.
It reminds us that developing AI isn't just about the technical side. We need to think about the broader impact these technologies have on society. Let's move on to a paper that looks at how LLMs can improve code generation. Chain of grounded objectives, bridging process, and goal-oriented prompting for code generation. Can you break down the core idea here?
This research is all about making code generation more efficient and effective by combining the best aspects of two common approaches: process-oriented prompting and goal-oriented prompting.
So it's not just about teaching LLMs to write code. It's about teaching them to write good code that actually solves the intended problem.
Exactly. Process-oriented prompting is like giving step-by-step instructions, while goal-oriented prompting is about specifying the desired outcome. They've come up with something called chain of grounded objectives, or CGO, to combine these approaches.
Okay, how does CGO work?
CGO embeds functional objectives right into the prompts. So it's like giving the LLM a roadmap that leads to the desired outcome, not just a set of directions.
So it's giving the LLM a better understanding of the big picture, the overall purpose of the code. Does this actually make a difference in the quality of the code that's generated?
Yes, their results show that CGO leads to significant improvements, addressing limitations of existing methods and producing code that's both better and more efficient. This has big implications for software development. It could make it much easier and faster to write good code, even for people who aren't expert programmers.
That's exciting to hear. It has the potential to make coding more accessible to a wider range of people. Now let's talk about a paper that looks at how we evaluate LLMs. ADIVAL, alignment-based dynamic evaluation to mitigate data contamination in large language models. What is data contamination, and why is it a problem for evaluating LLMs?
Data contamination is when irrelevant or unintended information sneaks into the training data, which can lead to models that are biased or inaccurate. And it's a huge problem for LLMs because they're often trained on these massive data sets scraped from the web, where it's almost impossible to completely avoid contamination.
So it's like trying to learn from a textbook that's full of errors. It can lead to a flawed understanding of the subject.
Exactly. This research introduces ADIVAL, which is a new way to evaluate LLMs that's more resistant to the effects of data contamination.
So instead of trying to clean the data itself, they're making the evaluation process more discerning, like a filter that can separate the signal from the noise.
That's a great way to think about it. ADIVAL does this by dynamically aligning the evaluation questions with the main concepts in the data. And it also uses online search to get more context and knowledge, ensuring the evaluation is based on a solid understanding of the topic.
It's all about giving the LM a fair and accurate test. So what were the results of using ADIVAL?
They found that it significantly reduces the impact of data contamination, leading to more accurate and trustworthy assessments of how well LLMs actually perform. This is crucial because we don't want to overestimate their capabilities or deploy them in situations where they might make costly mistakes.
It's a reminder that evaluating AI systems properly is just as important as developing them in the first place. Okay, let's move on to a paper that delves into a fundamental aspect of language processing, a comprehensive framework for semantic similarity detection, using transformer architectures and enhanced ensemble techniques. Can you walk us through what semantic similarity detection is and why it's a significant challenge for natural language processing?
Semantic similarity detection is all about figuring out how similar two pieces of text are in terms of their meaning, even if they use different words or phrasing. Think about a search engine that can understand that how to bake a cake and cake recipes are basically asking for the same thing.
So it's about teaching AI to go beyond the literal words and grasp the underlying meaning and intent.
Exactly. This research uses a teacher-student model approach that takes advantage of transformer architectures. Specifically, they use Deberta v3 large and Mamba 790 meters. The teacher model is trained on a massive data set to develop a deep understanding of semantic relationships, and then it guides the student model, which is designed to be more efficient, especially for shorter texts.
It's like a master craftsman training an apprentice.
Exactly. They also use techniques like domain adaptation and data augmentation to make the model more adaptable and robust.
How does this approach compare to other methods?
Their framework outperforms other methods, demonstrating its effectiveness in detecting semantic similarity accurately and efficiently, even in those tricky cases where the wording might be very different. This research is a step towards language processing systems that can truly understand the nuances of human communication.
It's fascinating to see how these advances are bridging the gap between how humans and machines communicate. Now, let's look at a paper that examines a crucial factor that can influence how well LLMs perform. Clear minds think alike. What makes LLM fine-tuning robust? A study of token perplexity. Can you explain token perplexity and why it matters for fine-tuning LLMs?
This research digs into what makes LLM fine-tuning robust. Fine-tuning is basically adapting a pre-trained LLM for a specific task or domain. Their big finding is that the robustness of that fine-tuning process is strongly linked to something called token perplexity in the training data.
Remind me, what's perplexity again?
Perplexity is essentially a measure of how predictable a sequence of words is. Lower perplexity means the model is pretty confident about predicting the next word, while higher perplexity means there's more uncertainty. Think about the difference between reading a predictable children's book versus a complex scientific paper.
So they're saying that using data with lower perplexity for fine-tuning leads to LLMs that are more adaptable and can handle a wider range of situations.
Precisely. They found that when you fine-tune with data that has a lot of high perplexity tokens, the model's performance drops significantly when you test it on data that's outside of its training domain.
So if you train an LLM on a very predictable and narrow data set, it might struggle to handle new and unexpected language patterns. It's like a student who's only ever studied one subject and then struggles when they encounter something new.
That's a good analogy. Interestingly, they also found that fine-tuning with data generated by another LLM, which usually has lower perplexity, can make models more robust.
So AI-generated data can actually be used to make other AIs more adaptable. What other strategies did they explore?
They found that simply masking those high perplexity tokens in the original training data can have a similar effect to using LLM-generated data. This suggests that it's not just about where the data comes from, but also about how predictable and clear it is.
It seems like there's a lot we can learn from these insights to make LLMs more reliable and capable of handling a broader range of tasks. Now, let's move on to a paper that looks at language processing for a specific language. Idiom detection in Sorani Kurdish texts. What are idioms, and why are they so tricky for language models?
Idioms are phrases where the meaning of the whole phrase is different from the literal meaning of the individual words. Like, kick the bucket doesn't actually mean kicking a bucket, it means to die.
Right.
They're tough for language models because they rely on understanding cultural context and subtle nuances of language.
We're like linguistic puzzles that require more than just a dictionary definition to understand.
Right. This research focuses on detecting idioms in Sorani Kurdish, a language spoken by millions of people. They built a new data set with over 10,000 sentences containing 101 different Sorani Kurdish idioms used in different contexts.
So they're essentially teaching AI to understand the colorful expressions and figures of speech that are unique to this language.
Exactly. They tested 3 different deep learning models, and they found that the best one, a transformer model based on Kubert, was able to detect these idioms with nearly 99% accuracy.
That's really impressive. It's encouraging to see these advancements being applied to languages that haven't received as much attention in the AI world. This could lead to better machine translation, sentiment analysis, and even tools for cultural preservation. Now, let's look at a paper that challenges LLMs with a very specific task: investigating the decomposition capabilities of large language models in natural to formal language conversion. Can you explain what this task involves and why it's so difficult?
Natural to formal language conversion is all about translating everyday human language, which is full of ambiguity and context dependence, into a precise formal language, like logic or code. Think about translating the question, "What's the capital of France?" into a database query.
It's about bridging the gap between the way humans naturally communicate and the strict rules of formal languages.
Exactly. This research dives into how well LLMs can handle this conversion process, focusing on their ability to break down complex expressions, decomposition, and then assemble them into formal representations, composition.
It sounds like a very demanding task, requiring a deep understanding of both natural and formal languages.
Yes, it is. They created a framework called DEDC to evaluate these capabilities, and what they found is that even the most advanced LLMs still struggle with both decomposition and composition. They make mistakes, revealing that they haven't fully grasped the nuances of these complex tasks.
So while LLMs have made incredible progress in understanding language, there's still room for improvement when it comes to these more intricate translation tasks.
Absolutely. This research helps us understand the current limitations of LLMs, which is essential for guiding future research and development in this area.
It's a reminder that even the most impressive AI systems are still works in progress. Okay, let's move on to a paper that revisits a topic we touched on earlier: rethinking table instruction tuning. Didn't we already talk about a paper that involved tables?
Yes, but this one digs deeper into the specifics of how we teach LLMs to understand and reason about data in tables. They're actually questioning the effectiveness of some commonly used methods.
So they're refining those techniques to make sure LLMs can become real experts at handling tabular data, which is often used to represent information in a structured way.
Exactly. They found that some of the existing approaches can lead to overfitting, where the model becomes too specialized to the specific data it was trained on and loses some of its general capabilities. Imagine teaching an LLM to understand tables about baseball statistics, but then it struggles when you show it a table about financial data.
It's like it becomes a one-trick pony.
Oh, for sure.
So they're looking for a more balanced approach to instruction tuning, making sure the LLM doesn't lose its general intelligence while becoming a table expert.
Precisely. They're looking for a more balanced approach that helps the LLM become a table expert without losing its general knowledge. And their research suggests that using smaller learning rates and actually less training data can lead to better table understanding while keeping that broader intelligence intact.
So it's about finding that right balance. Did they propose any specific methods based on these findings?
They did. They introduced HEMA, which is a new table instruction-tuned LLM. What's interesting is that it outperforms existing models on those table-related tasks, but it also maintains really good general language abilities. This shows the potential of this more balanced fine-tuning, where you enhance specific skills without sacrificing that overall flexibility.
It's like teaching someone to be a great chef without taking away their ability to learn other things. Okay, let's talk about comparable corpora, opportunities for new research directions. This one seems different, almost like a research proposal rather than specific findings.
You're right, it is. This paper focuses on something called comparable corpora. These are collections of texts in different languages, but they all cover similar themes or areas. Like, imagine you have news articles in English and Spanish, both reporting on the same event.
So they're not direct translations, but they're exploring the same ideas from different linguistic viewpoints. What kind of opportunities do these comparable corpora offer for AI research?
The authors highlight several possibilities. They argue that these types of corpora can be used to develop AI models that can understand and work with multiple languages, improve machine translation, and even give us deeper insights into the similarities and differences between languages.
It's like using these parallel universes of language to unlock a deeper understanding of how humans communicate. Okay, let's move on to a paper that tests AI's abilities in a crucial area for healthcare: evaluating computational accuracy of large language models in numerical reasoning tasks for healthcare applications. Why is this numerical reasoning so important in healthcare?
Numerical reasoning is essential in healthcare because it involves understanding and working with numbers. Think about calculating dosages, interpreting lab results, or assessing a patient's risk factors. All these tasks require precise numerical understanding.
So they're basically seeing if LLMs can handle the quantitative challenges of the medical world. What do they find out?
They created a special data set with 1,000 numerical problems specifically related to healthcare, and they tested a refined LLM based on the GPT-3 architecture. The results were promising. Overall, the LLM got 84% of the answers right, but it struggled with more complex problems that required multiple steps of reasoning.
So there's potential there, but we're not quite ready to hand over those life or death calculations to AI just yet. What do they suggest to improve the model's performance?
Interestingly, they found that adding a fact-checking step significantly boosted the accuracy. This emphasizes the need for checks and balances, especially in healthcare, to make sure these systems are reliable before we start using them in real-world settings.
Absolutely. It's about using AI safely and responsibly. Now, let's talk about a paper that introduces a new way to test LLM's mathematical reasoning skills. The CARP dataset. What's special about this dataset, and why is it important?
This dataset is designed to really challenge LLMs to see if they can grasp some pretty advanced mathematical concepts. It's named after Richard Karp, a famous computer scientist known for his work on things like computational complexity. The Karp dataset consists of these detailed proofs of NP completeness reductions. These are fundamental concepts in theoretical computer science.
It sounds like a test for AI geniuses. So how did the LLMs do on this challenge?
Well, the initial results showed that state-of-the-art LLMs struggle with these really tough reasoning tasks. However, they also discovered that when they specifically trained LLMs on the CARP dataset, their performance improved considerably. This suggests that with the right training, these models can learn to understand and work with even these abstract mathematical ideas.
It's exciting to imagine a future where AI could help mathematicians and computer scientists solve complex problems, prove theorems, maybe even discover new mathematical concepts. Now, let's look at a paper that tries to improve how we convert spoken language into written text. Recording for eyes, not echoing to ears. Contextualized spoken-to-written conversion of ASR transcripts. What's the motivation behind this research?
Automatic speech recognition, or ASR, is really good at transcribing what people say, but those raw transcripts aren't always that easy to read. They're often full of filler words, grammatical errors, and incomplete sentences. Imagine reading a transcript of a casual conversation. It would be full of ums, ahs, and unfinished thoughts.
So they're working on making those transcripts more readable and polished.
Exactly. They call this new task contextualized spoken-to-written conversion, or CoS2W. It's about transforming those messy ASR transcripts into formal, readable text without changing the meaning.
It's like having an AI editor to clean up those transcripts and make them easier to understand. Do they develop any specific techniques for this?
They did. They created a new dataset called SWAB to test how well different LLMs can handle this RS2W task. The results show that LLMs can do a pretty good job. They can improve the grammar, formality, and readability of those transcripts without changing the original message.
This could be incredibly useful for things like generating meeting minutes, creating subtitles for videos, or making spoken content accessible to people with hearing impairments. It's all about using AI to bridge the gap between spoken and written language, making information more accessible. Okay, let's explore a paper that looks at the potential and the challenges of using LLMs for a very specific task. The Promises and Pitfalls of LLM Annotations and Dataset Labeling, a case study on media bias detection. What are some of the issues with using LLMs for something as complex as detecting bias in the media?
Media bias detection is a really tricky problem. It involves recognizing subtle language cues and framing techniques that might reveal a particular slant or perspective in news articles or other media content. This research looks at using LLMs to label datasets that are then used to train other AI systems to detect bias.
So you're using one AI to train another AI to identify bias. That's fascinating. What are the potential benefits and drawbacks of doing this?
Their research showed both pros and cons. On the one hand, LLMs can be pretty good at labeling data for this task, which could speed up the development of media bias detection systems. But here's the catch. LLMs themselves can have biases, and those biases can show up in the labels they create.
It's like the saying garbage in, garbage out. If the LLM is trained on biased data, it's going to produce biased labels.
Exactly. They stress the importance of carefully examining the biases of both the LLMs that are doing the labeling and the models that are being trained on those labels. We need human oversight to ensure that these AI systems are fair and unbiased.
It's a reminder that AI development isn't just about making things work, it's also about making sure they're working in a way that aligns with our values. Okay, let's move on to a paper that improves how LLMs interact with a specific type of database. AutoCipher. improving LLMs on cipher generation via LLM-supervised generation verification framework. What's cipher, and how does this research make it easier to use?
Cipher is a special language used to query graph databases. These databases store information in the form of nodes and relationships, representing connections between things. Imagine a database of a social network where people are nodes and their friendships are the relationships.
So instead of the traditional rows and columns, these databases are more like a network of interconnected things.
Exactly. Cipher is how you ask questions and retrieve information from these databases, but translating natural language into cipher queries can be difficult. This research introduces AutoCipher, which uses LLMs to do this translation automatically.
So you can just ask a question in plain English, and the LLM will figure out how to write the cipher code to get the answer.
That's the idea. And they've developed a clever system to ensure the accuracy of those queries. They also created a new dataset called SynthCipher, with over 29,000 examples of natural language and cipher pairs, which they use to train and test their models.
This could make graph databases much more accessible to people who don't know how to code, opening up possibilities for things like social network analysis, bioinformatics, and financial modeling. Now, let's look at a paper that's all about improving the quality of the data used to train LLMs. ResoFilter, fine-grained synthetic data filtering for large language models through data parameter resonance analysis. What role does synthetic data play in training LLMs, and how does ResoFilter improve this process?
Synthetic data, which is basically artificially generated data, is becoming more and more important in AI. LLMs can actually generate entire datasets of synthetic text, which reduces the need for collecting and labeling real-world data. But the quality of synthetic data can be all over the place, and that can impact how well the models trained on that data perform.
It's like the difference between studying from a well-written textbook and studying from a bunch of random notes. The quality of the source material really matters.
That's a good way to put it. ResoFilter acts like a filter, making sure the synthetic data is high quality. It analyzes how well the data aligns with the LLM's internal parameters during the training process.
So it's like the LLM is giving feedback as it learns, saying, this data is helping me or this data is confusing me.
Exactly. And what they found is that ResoFilter can pick out the best synthetic data, leading to results that are just as good as if you used a much larger dataset.
Hmm.
This could make LLM training more efficient and less reliant on those massive real-world datasets.
It could really change the game for researchers and developers who might not have access to huge amounts of data. Okay, let's talk about a paper that tackles the problem of predicting future trends. Freeformer, frequency-enhanced transformer for multivariate time series forecasting. What's time series forecasting all about, and how does Freeformer improve it?
Time series forecasting is basically predicting what's going to happen in the future based on what's happened in the past. Think about predicting stock prices, the weather, or even someone's health based on historical data. Freeformer uses transformer architectures, which have been really successful in language processing, and applies them to time series data.
So they're using these models that are good at understanding language to predict patterns in numerical data over time. What's the secret sauce in Freeformer?
The key innovation is frequency analysis. Instead of just looking at the raw time series data, Freeformer transforms it into the frequency domain using something called the discrete Fourier transform. It's kind of like listening to a piece of music and figuring out all the individual notes or frequencies that make it up.
So they're looking at the underlying rhythms and cycles hidden within that data, which might not be obvious when you just look at the numbers themselves.
Exactly. And their results show that this approach leads to much more accurate forecasts. Freeformer outperformed other models across a variety of different data sets.
This has some really interesting potential applications in fields like finance, meteorology, and even personalized medicine. Okay, let's move on to a paper that explores the world of surrogate models. Transfer learning of surrogate models via domain-affine transformation across synthetic and real-world benchmarks. Can you explain what surrogate models are and how this research improves how we use them?
Surrogate models are basically simplified versions of more complex systems or processes. We use them when it's too expensive or time-consuming to work with the real thing. Imagine using a computer simulation to study the aerodynamics of an airplane wing instead of building and testing a real physical model.
So they're like efficient stand-ins that let us experiment and learn without all the real-world costs and risks.
Exactly. This research is about transferring knowledge from existing surrogate models to new tasks or situations using a technique called transfer learning.
So instead of building a new surrogate model from scratch for every new problem, we can repurpose and adapt existing models, saving a lot of time and effort.
Precisely. Their method focuses on transferring these non-differentiable surrogate models, in this case, random forests. They assume that the tasks are related by a specific mathematical transformation, and then they use a little bit of data to figure out that transformation and adapt the existing model.
It's like taking a blueprint for a building and modifying it to fit a different location.
Perfect analogy.
Yeah.
And what they found is that this transfer learning approach really works. It significantly reduces the amount of data and computing power needed to build these surrogate models, especially in complex real-world scenarios.
This could be a big deal for fields like engineering, science, and finance, where surrogate models are used all the time.
Huh.
Okay, let's talk about a paper that takes a more critical look at an AI technique we discussed earlier, GraphRag under fire. I remember we talked about GraphRag, but this research seems to focus on potential weaknesses.
You're right. Earlier research showed how effective GraphRag is for improving things like question answering and text generation. But this paper looks at its potential security vulnerabilities. Specifically, they look at how susceptible it is to something called poisoning attacks.
Remind me, what's GraphRag?
GraphRag takes those retrieval augmented generation systems, or RAG systems, and supercharges them by structuring external knowledge in a graph format. It's like giving an AI system access to a huge network of interconnected facts and concepts to draw from when answering questions or generating text.
So it's like a knowledge superhighway for AI, but how do these poisoning attacks work?
Poisoning attacks target that knowledge graph, injecting false information to try and manipulate the AI's responses. Imagine someone sneaking a fake fact into Wikipedia, which then gets picked up by the GraphRag system, leading to incorrect or misleading answers.
It's like contaminating the well of knowledge that the AI is drawing from. Did they find any significant weaknesses in GraphRag?
They actually found a bit of a paradox. Because of its graph-based structure, GraphRag is more resilient to simple poisoning attacks than traditional RGAS systems, but this same structure also opens up new vulnerabilities.
So it's a trade-off.
Hmm.
A more complex system might be harder to attack in some ways, but could also have new weaknesses. It's like a fortress with stronger walls, but maybe a hidden backdoor.
Exactly. They developed a new type of attack called grag poison, which takes advantage of the way the knowledge graph is connected to inject false information that can affect multiple queries.
This emphasizes the need to think about security from the ground up as we build these increasingly complex AI systems.
All right, let's look at a paper that gives AI systems a more active role in keeping an eye on things. Argos, agentic time series anomaly detection with autonomous rule generation via large language models. What does it mean for an anomaly detection system to be agentic, and how does Argos achieve this? Anomaly detection systems are used to spot unusual events or patterns in data that's collected over time. Think about a system that monitors network traffic to detect cyber attacks, or a system that tracks a patient's vital signs to detect medical emergencies.
So they're like digital detectives constantly scanning for anything out of the ordinary.
Exactly. Traditionally, these systems rely on rules or thresholds that are set by humans. But those rules can be too rigid and hard to maintain as the patterns they're trying to detect change.
So they're giving these systems more intelligence and independence to adapt to those changing conditions, making them more proactive and effective.
Precisely. Argos does this by using LLMs to automatically generate its own anomaly detection rules. Instead of just relying on what humans tell it to look for, Argos analyzes past data, figures out the patterns, and creates its own rules for what's considered normal and what's considered an anomaly.
It's like they've given it the ability to learn from experience and become a more sophisticated detective. So how well does Argos actually work?
It performs really well. They tested it against other methods, and Argos consistently came out on top, both in terms of how accurately it detects anomalies and how efficiently it does it. This could have a huge impact in areas like cybersecurity, fraud detection, and even healthcare.
It's a really impressive example of how AI can take on more responsibility and help us manage those complex systems that are constantly evolving. Okay, let's dive into a paper that combines two important concepts in deep learning. Active learning for continual learning, keeping the past alive in the present. Can you break down these concepts for us and explain why combining them is so beneficial?
Continual learning is the ability of an AI system to keep learning from new data without forgetting what it's already learned. It's like the difference between a student who crams for a test and then forgets everything versus a student who builds a solid foundation of knowledge over time.
So it's about creating AI systems that are lifelong learners, just like humans.
Yeah.
And what's active learning all about?
Active learning is about choosing which data to learn from in a smart way. Instead of just passively absorbing everything, it's about actively seeking out the most useful and informative data points. It's like a student asking the teacher for clarification on the most challenging concepts.
So they're teaching AI systems to be more strategic and efficient in their learning. They need to remember the past and also actively seek out new knowledge that will help them grow.
Exactly. This research introduces a framework called AccuACL that combines active learning with continual learning. They use a mathematical tool called the Fisher Information Matrix to figure out which data points are the most informative and guide the learning process.
It's like giving the AI system a sense of curiosity, so it's always looking for new insights to improve its understanding. So how well does this approach actually work?
They found that AccuACL outperforms those traditional active learning methods, showing how effective it is to balance the need for both new information and retaining that past knowledge. This brings us closer to AI systems that can adapt and learn continuously throughout their lifetime, just like we do.
It's a step towards AI that's more aligned with the way humans naturally learn and evolve. Okay, let's move on to a paper that focuses on a specific type of cyber attack, an efficient real-time DDoS detection model using machine learning algorithms. Can you explain what DDoS attacks are and how machine learning can help defend against them?
A distributed denial of service attack, or DDoS attack, is like a digital traffic jam, except it's intentionally created. It's when attackers flood a server with so much traffic from different sources that it becomes overwhelmed and can't respond to legitimate requests. Think about a website crashing because it's suddenly bombarded with requests.
So it's a way to take a server offline by overwhelming it with traffic. How does machine learning come into play here?
Machine learning can analyze patterns in network traffic to spot those telltale signs of a DDoS attack in real time. This allows for quicker detection and response, limiting the disruption caused by the attack.
So it's like having AI traffic cops that can direct the good traffic and block the bad traffic. What machine learning algorithms did they find most effective?
They tested a bunch of different algorithms and found that random forest, AdaBoost, and XGBoost worked the best. These algorithms were highly accurate and efficient in catching those DDoS attacks.
It's good to know that researchers are developing these tools to make our online world safer. Okay, let's talk about a paper that tackles the black box problem in AI, relative layer-wise relevance propagation, a more robust neural network's explainability. What is the black box problem, and what's this new technique all about?
The black box problem is this. A lot of deep learning models are opaque. We can see what goes in and what comes out, but it's hard to understand how the model actually makes its decisions. Imagine a medical diagnosis system that gives you a diagnosis but can't explain how it arrived at that conclusion.
It's like having a brilliant doctor who can't articulate their reasoning. It's hard to trust something when you don't understand how it works.
Exactly. This research introduces relative layer-wise relevance propagation, or RLRP. It's a way to explain how those neural networks make decisions.
So they're cracking open that black box and shining a light on the inner workings of these systems.
Precisely. RLRP analyzes how each individual feature contributes to the final output. It's like tracing the path of information through the network and highlighting the most important parts. Imagine you have a chest x-ray, and the system can highlight the specific areas that led to the diagnosis of pneumonia.
That kind of transparency would be incredible in fields like healthcare, finance, or any area where understanding the AI's reasoning is crucial for trust and decision-making. Okay, next up is a paper about a special type of reinforcement learning, fat-to-thin policy optimization, offline RL with sparse policies. Can you unpack those terms for us?
Offline reinforcement learning, or offline RL, is about training an AI agent using a dataset of experiences instead of letting it directly interact with the environment. Think about learning to play chess by studying a database of games rather than actually playing against someone.
So it's a less interactive, more book learning approach to reinforcement learning. And what are sparse policies?
A sparse policy is one where the AI's actions are limited. Think of a robot that can only move in 4 directions, or a medical treatment system that can only choose from a limited set of drugs.
So you're restricting both how the AI learns and what it can do. What's the advantage of that?
It makes it possible to teach the AI safe behaviors entirely from existing data. That's really important for things like healthcare and self-driving cars, where real-world experimentation could have dangerous consequences. Imagine training a self-driving car to avoid accidents by using a data set of driving scenarios without actually putting it on the road and risking collisions.
So it's about learning to be safe without taking those real-world risks. How does this fat-to-thin policy optimization work?
What they do is maintain a fat policy during training, which explores a wide range of actions. Then they distill that down to a thin policy, which is the limited set of safe actions that the AI will actually use in real-world situations. It's like considering all the possibilities, but ultimately choosing the safest and most reliable course of action.
It's a clever way to balance exploration and safety. Now, let's explore a paper that takes a non-invasive approach to diagnosing a neurological disorder, distinguishing Parkinson's patients using voice-based feature extraction and classification. How can something as simple as voice analysis be used to detect Parkinson's disease?
Parkinson's disease mainly affects movement, but it can also cause subtle changes in a person's voice. This research explores the idea of using voice analysis as a non-invasive way to diagnose and monitor the disease.
So they're literally listening for clues in a person's voice that might indicate Parkinson's.
Exactly. They recorded speech samples from both Parkinson's patients and healthy people, and they extracted 19 different features from those samples.
What kind of features?
Things like variations in pitch and loudness, measures of vocal tremors and breaks in speech. These are subtle things that might be hard for humans to pick up on consistently.
Right, so they're using AI to detect those subtle patterns in the voice. What do they find?
They trained several different machine learning algorithms to classify those speech samples based on the extracted features, and they found that a 3-layer artificial neural network was the most accurate, able to distinguish between Parkinson's patients and healthy people quite effectively.
That's really encouraging. This could lead to earlier and easier diagnosis of Parkinson's, which is crucial for managing the disease. Okay, let's move on to a paper that explores the theoretical foundations of a popular type of AI model: convergence of gradient-based training for linear graph neural networks. What are graph neural networks, and what does this research tell us about how they learn?
Graph neural networks, or GNNs, are specialized neural networks that are designed to work with data that's structured like a graph. Think about things like social networks, where people are nodes and their connections are edges, or molecules where atoms are nodes and their bonds are edges. GNNs are really good at understanding these types of relationships and patterns.
So they're like AI systems that are built to navigate and learn from the interconnected world of networks and relationships. What does this particular research paper investigate about GNNs?
This paper is all about convergence in the training process for linear GNNs. Convergence basically means that the training process reaches a stable point where the model stops getting better. Think about climbing a mountain eventually, you reach the peak, and there's nowhere higher to go.
So they're trying to understand the mathematical guarantees that these GNNs will actually learn effectively and reach a stable solution.
Exactly. And they were able to prove that when you train a linear GNN using a specific type of loss function, it will always converge to the absolute best solution.
It's a really important finding because it helps us understand why GNNs have been so successful in various applications. Okay, let's talk about a paper that focuses on protecting data privacy. Optimal strategies for federated learning maintaining client privacy. What is federated learning, and how does this research make it more secure?
Federated learning, or FL, is a way for multiple clients, each with their own local data, to work together to train a shared AI model without actually sharing their data with each other. Think about hospitals around the world collaborating to train a model to diagnose a rare disease, but they don't want to share their sensitive patient data.
So it's a collaborative learning process where everyone benefits from the shared knowledge while keeping their individual data private.
Exactly. This research looks at the trade-off between model performance and privacy in federated learning. They analyze how different training strategies affect both the accuracy of the final model and the protection of the client's data.
It's a delicate balance. You want the benefits of collaboration without compromising privacy.
Precisely. And their research provides valuable guidance on how to find those optimal strategies. This is essential for enabling AI applications in sensitive areas like healthcare and finance, where privacy is absolutely paramount.
It's really encouraging to see research like this showing how we can push the boundaries of AI while also upholding ethical principles and protecting people's privacy. It's been a fascinating journey diving into all this cutting-edge AI research. It's clear that AI is rapidly evolving, impacting virtually every field imaginable, and raising crucial questions about how we develop and use these powerful technologies responsibly. As we continue to explore the possibilities of AI, let's remember to do so with a thoughtful and ethical approach, ensuring that these advancements ultimately benefit humanity.